Welcome back, AP Stat students, for another episode of Regression. So today we're going to finish lesson 3.3, and you're going to learn how to make residual plots. Okay, we're going to start with a little bit of review, practice, kind of dig into what we did last time, because as I mentioned before, it's really important that you get quite good at it, and then we'll get to the residual plots. So let's start with an example. Okay, I have some data here recording the number of years a person has smoked and the damage they've done to their lungs. Okay, I already mentioned in the data, we're going to call years the explanatory variable and damage the response. But if I hadn't have told you that, hopefully you could figure that out on your own, that the number of years a person smokes will typically explain the amount of damage they've done, right? So enter the data in your calculator, and we're going to answer a bunch of questions. Okay. We're kind of walking through what you should be doing when you have bivariant data. So step one, you're going to graph it, look at it, describe the data set. Then assuming that you have a linear relationship, you're going to go ahead and calculate the correlation and the coefficient of determination. And then since this problem has context, right? X and Y have real world meaning. We're going to describe what the correlation and the coefficient of determination mean in terms of these real world variables. Then we'll calculate our least squares regression line. And we're going to say why it's the best fit line. And then, of course, it's linear. So it will have a slope and a y-intercept. But again, we have context here. So we're going to describe what that tells us in terms of our variables. Then we're going to do some predictions. And we're going to talk about these predictions when we do them. And then the new thing, down here, we're going to make a residual plot and describe what it tells us. All right, so step one, let's just graph it. So your graph should look something like that. Okay. It's not a ton of data, so it's really hard to tell, is it linear, is it curved? Hard to tell for sure. But I think we can all agree there's definitely a positive association, right? As a person spends more years smoking, we see more damage to their lungs. So it's hard to tell with that small of a data set if it's linear or curved, but let's proceed. So step two, let's find our correlation and our coefficient of determination, and then let's describe in words what they mean. So we're just going to do a little linear regression. And again, I'm using this one just because our formula sheet calls B the slope. I have the data in list 1 and list 2. And I'm going to store that equation. So variables, y variables function, and I'll store it as y sub 1. Okay, there we go. There's our correlation. Okay, 0.88, 0.89. And there's our coefficient of determination, 0.78. So that correlation, what does that tell us? Okay. That coefficient of determination, what is that telling us? All right, so we see a moderately strong to strong positive correlation. And we see that approximately 78% of the lung damage that we observe can be explained by the number of years a person smokes. Okay. All right. Find the least squares regression line. Well, there it is. We have that on the same screen. Okay. So our slope is approximately 1.85, and our y-intercept's negative 10.7. All right, now in context, what does that slope tell me? Okay, well, that tells me it's a rate of change, right? A slope. So for every year a person smokes, that's how much more lung damage they would expect. About 1.85% more damage to the lungs. What does the y-intercept mean in context? Well, this would be for a person that doesn't smoke, they have negative lung damage. That's what it's telling me, right? Somebody who smokes for 0 years, they have negative 10.7% lung damage. Okay, that doesn't make sense. And let's kind of investigate why. So I'm going to go back to my graph, right? So this is my graph when I do a zoom stat. And the calculator's doing a good job, right? It's framing the data so that I don't have a lot of blank space on either side of the graph. That's a good thing. However, you'll notice, right, when you trace the line, by the way, I'm going to jump off of the point and onto the line with an up arrow, right? You trace that line, and you'll notice my cursor, it's going to go right off the graph as I head back towards the y-intercept. And that's really the explanation. That's why we're getting this kind of nonsensical y-intercept. Because there's no data over there, right? Our lowest data point is for a person who smoked 9 years. There's our lowest data point. So once I start going further and further back, I'm leaving reality behind. Okay, we have a name for this. It's called extrapolation. So that word again, extrapolation. So as we go outside the domain of our data set, we're extrapolating. And the further we extrapolate, we're leaving reality and we're going into like fantasy land, okay? So it's not possible for a person to have negative 10% lung damage because they didn't smoke. The reason I'm getting a number like that is because I have no data in that vicinity. So if I cared more about people who didn't smoke and the condition of their lungs, then I need to get data on people who didn't smoke. And if I did that, I'd get a completely different line and it wouldn't be so nonsensical. Okay, so that's an important point. Extrapolation. All right, let's do some predictions. So number 4, we want to predict the percentage of lung damage for someone who smoked for 30 years. Okay, so we go back to our equation. I didn't write it down. I probably have it on a slide, but okay, so there's my equation. And 30 years. So I put 30 in there for X. Okay, and that'll give me my prediction. You could put a subscript on here, y hat sub 30, telling me, hey, I'm predicting for 30 years, right? Now, notice when I'm working it out here, obviously I have to round the numbers off to, at some point. If I want it to be a little more accurate and also faster, remember, I stored that equation. So I could look at my graph and trace it, again, get onto the actual line, and I could trace that thing until I got to 30 years. That'd be kind of cool. And you could see that my line at 30 years is predicting, somewhere between 44 and 45% lung damage. Okay, that's pretty cool. But I could be more accurate. I could zoom in, or I could, above traces the calculate, I could calculate. Real cool stuff. Some of this is, calculus stuff, but I could calculate a value, and I could just put in 30 years for X, and it'll jump right there. And there we go. So my line, my least square regression equation, would predict 44.8% damage. There's another way I could get it, though. Remember, I have, again, the equation stored as a function, so I could go to variables, Y variables, function. That's where it's stored, and I could tell the calculator, plug 30 into that function for me and see what we get. And there you go. Another quick way to do it. So you do need to show this work if this were a test question, right? Write your equation, plug in 30, and then just jump to your calculator, and there's your answer. So 44.8% for a person who has smoked 30 years. Okay, now question number 5. This is one that a ton of students miss. Notice, we are now trying to predict the number of years somebody smoked. You see how that's different, right? Our relationship was the years were explaining lung damage. Now we're looking at lung damage and we're trying to work backwards and explain how many years a person has smoked. So you see, we've reversed the explanatory response relationship here. So I have to stress this. The equation that I just used on number 4 cannot be used on number 5. Say that again. The equation I just used on number 4 cannot be used on problem 5 because we've reversed the x and y. We've changed explanatory and response. And some students will scratch their head. Well, why? How come? Remember, least squares regression minimizes vertical distances. Vertical distances. Does not minimize horizontal distances. So when I switch my x and y axes, right? I've now switched vertical and horizontal. They've changed places. So this equation here does not work when I've switched the x and y axes. So I have to make a whole new equation. But it's not hard. It's just most students don't think about that. Most students are used to, algebra 1 and calculus, and they just go, oh yeah, just plug into the y value. Well, in statistics, doing regression, you're never allowed to plug into the y value. You can only plug into your x value, your explanatory variable, never to your response, okay? So let's do this problem again. And this time when I calculate, I have to reverse the explanatory and response variables. And I'll store this, but I'll store it in a different location. Okay, so here's my new equation. And when I write this one out, instead of saying y hat and x, because now I've switched x and y, I'm going to use something that's a little bit more accurate, so I don't get confused. Okay, so my y value is now the years of smoking. So I'll say years approximately equal to 10.1 plus 0.42 multiplied by the lung damage. Okay, so there's my new equation that I can use for this problem. And in the future, feel free to not even use y hats and x's. You can always label the variables so you don't get confused. Now, some of you might think, well, why am I allowed to switch this explanatory response relationship, right? That's a reasonable question because really it should be the year of smoking explains the damage done. But there are some instances you could think about. Maybe you are a coroner and you're doing an autopsy on a person. Well, now you can't say, hey, how many years did you smoke, right? All you can do is look at their lungs, and then you would use the lungs to try to predict how many years they smoked. So we could think of some instances where maybe this reverse relationship does make sense. Okay, so anyway, let's use that equation and let's put 58 and see what we get. Okay, work that out. Again, I'm going to just take the shortcut. And also, again, make sure, since this is functional notation, that you're using the parentheses, okay? Because we're not saying y sub 2 multiplied by something. We're saying plug something into that function that we've stored in y sub 2. And there we go. Approximately 34.7 years of smoking would be predicted. Okay? Now, I really want to stress, I'm going to write that down. Approximately 34.7. I really want to stress that's the correct answer. I'm going to go back and do the problem incorrectly just to show you. You know, what if a student had used this first equation here and they found the y, they plugged in 58 for the y value, okay? So this is the wrong way to do it, but just want to illustrate you will get a different answer. Okay, so okay, so see, you get a different answer. And yeah, I know that I rounded that off a lot. If you did it keeping all of the decimals intact, you're still going to get a different answer. Are there times where you might get the same answer? Of course, coincidences happen, but rarely will you get the exact same answer. Very rarely. So do it correctly. Remember, there's an explanatory and a response. We can predict the response from the explanatory. We can't go the other direction. Okay, really, really common mistake. All right, let's move on to number 6. Predict the percentage of lung damage. So we're going back to our original relationship where lung damage is the response. Okay, so we're going to go back to this equation from number 4. Okay, work that out. And we get over 100%. Now, does that mean I miscalculated? Because my common sense tells me that's not possible. Unless maybe they got a lung transplant and they're already destroying their new lung. Or lungs, I don't know. But no, I didn't make a mistake. And yeah, it doesn't really make sense. Now, again, how come I could get such a nonsensical answer? Think back to your graph. Whoops. Notice I have that other equation in there. That is this guy. So if you don't want it showing up on your graph bothering you, but you don't want to delete it, put your cursor on the equal sign, hit enter, and see now it's still saved, but it's not going to actually show up on your graph. Okay, so going back to my graph, again, I have this window, and it's a nice window. But once I go to 60 years, right, I'm outside the window. I'm going beyond the largest X value I have in my data set is 41 years of smoking. Now, does that mean it's impossible to smoke more than 41 years? I would say not, right? Plenty of people, you know, they've got the great Aunt Edna that, hey, I smoked my whole life since I was a kid and I'm still around, right? I mean, it's possible that that could happen. But I don't have any data in that region. So again, this line starts to carry off into fantasy land. And that's what's happening. At some point, I am extrapolating so far that I'm getting nonsensical results. Okay, so I would still say I'm predicting 100%, but it's extrapolation, so I know this prediction is very likely inaccurate. Okay. All right, so we'll get to number 7 in a little bit. I want to go over some more vocabulary and such before we actually do number 7. Okay. So here was the plot. And these we calculated. There's our equation. And we talked about how we got this nonsensical y-intercept. It doesn't mean we miscalculated. Again, it's due to extrapolation. And we did this, and again, we just did number 6, and we said this nonsensical answer was not a miscalculation, it was due to extrapolation. And so that's why I wanted to get to this slide here. Okay. We've talked about extrapolation, okay? Going outside of the domain of the data. The further we extrapolate, the more likely we are to be inaccurate. Okay? So be careful. Whenever you do extrapolation, you really need to be careful, and you need to note that. You need to note, hey, I'm extrapolating here. I don't have a ton of confidence in this prediction. And again, you need to look at how far did you extrapolate, how reasonable is that answer, right? -% lung damage is unreasonable. Over 100% unreasonable. So look, looking at our line, if I tried to extrapolate to, hey, Uncle Fred smoked 42 years, do you think it's okay? It's probably reasonably accurate, right? But part of it is how far have you extrapolated? Okay, and also how strong is your correlation, right? The stronger the correlation, the more accurate your prediction. And then, of course, if you interpolate, right, interpolation, that's going to mean more accuracy, because now I'm using that regression equation to make predictions where the domain, where the x values, right, are represented in the calculation. So making predictions in here, I'm going to feel a lot more confident with those. They're much more likely to be accurate. Okay, so that's called interpolation. So anytime you guys make a prediction from here on out, you don't spit out the number and move on. You need to say, this prediction is interpolation with a strong correlation, so it should be fairly accurate. Or the prediction is interpolation, but I have a very weak correlation, so I'm not too confident in this prediction, right? Or I'm doing extrapolation, and I've extrapolated a long distance, and this is completely nonsensical. I have no confidence in this answer, right? Or I'm extrapolating a very short distance with a strong correlation. My answer seems reasonable, right? So you need to put a sentence on your predictions from here on out, and one of those two words needs to end up in your sentence. The appropriate one, of course. All right. So now we're on to question 7. Let's make that residual plot. Okay, so step 1, I need to calculate my residuals. Okay. And a residual, we mentioned this last time, it's another word for the error, right? The error. It's the vertical distance between a point and the least square regression line. So, right? This point right here, it's that vertical distance. That would have a positive residual, right? When I'm below the line, like this point right here, whatever that vertical distance is, that's its residual, and it's going to be negative because I take the point's y-coordinate minus the line's y-coordinate. Okay? So residual, error, they're synonyms. Okay, here's some things about residuals. The sum of the residuals will always equal 0 if you don't round, right? You might have some rounding, and so you get something slightly off from 0. But if you weren't to round, the sum will always be 0. It's a fact. Just like the least square regression line always goes through the point x bar, y bar. It's a property, mathematical property, always the case. So please, every year I'll ask questions, and the AP exam will ask questions, and students will start talking about, well, since the sum of my residuals is 0, that tells you nothing, okay? So don't go there. It's not an explanation for anything. It's a property. Okay. Now, the whole point of the residual plot. Here's how I read it. When I see a curved residual plot, I say the data isn't linear. Okay, we'll talk about that in a minute once we make a plot. We also look at the spread of the residual plot. So I might see what we call fanning, so an increasing spread, which means I have more accuracy for part of the domain of my variable and less accuracy for another section of the data. Okay, we've talked about outliers a little bit. Now I can really define an outlier as a point with a large residual, right? Positive or negative, so the absolute value is large. Versus what we call an influential point. An influential point is a long way away from the rest of the data in the horizontal direction. And typically it's going to pull the line, the least square regression line, towards itself. So it won't have a large residual. But it has a huge impact on the regression equation. So again, let me try to illustrate both of those real quick. So if I have some line and I got a lot of points, and then there's one point like that, okay? This would be an outlier. It has a large magnitude for the error, right? Long way away from all the other points in the same X vicinity. Okay. Versus, so I have like a big cluster of data here, and then a point over here. Okay, now, without this point, right, I really have pretty much no association, but with that point, all of a sudden, I would have a least square regression line that goes like that. That point has basically created this big negative slope, which wouldn't have been there without the point. Notice it doesn't have a very large residual because it's pulled the line towards itself. So that's an influential point. Okay. Over here, that's an outlier. Okay. That's how they're different. And it's easy to check. If I remove the point and recalculate, right, I'll get a completely different line. I'll get something that has a much closer to zero slope, and I'll have a very weak correlation. But with this point, I'll have a fairly strong correlation. All right, so let's actually do the residuals. Okay, so what I need to do is calculate my errors or residuals. And I showed you that before. We're gonna have an empty list. We're gonna highlight it. And then we're gonna define the list to take the y coordinate minus the predicted y coordinate at the corresponding x value. Okay, so the observed y coordinate is in list 2. Then we're gonna subtract the predicted y coordinate, so that comes from my regression equation. And I need the y coordinate at that same x, right? That's what makes it vertical distance. Oh, not 22. 22 would only work for the first point. That'll now cover all the points as it works down the list. Okay. And yes, there is a command in your calculator. It says resid. You can use that command if you prefer, but if you're going to use it, make sure you know how to use it, right? Make sure that your data is in the correct lists to use it properly. Otherwise, your calculator might be looking at the incorrect list. I like to type this in. It doesn't take me long, and this way I know I'm sending the calculator to the correct x and y values. Okay, and just like that, I've got my residuals. So let me walk you through this. The first point is 10 units below the line. That's what it's telling me. Let's look at my graph. Whoops. The points are not in order from left to right. So point number 1, let me go back. Point number 1 was 22 years of smoking. So let's find that point. Okay, so there's the point. So we're saying we're below the line by whatever units that said, right? And then we can go to our second point, right? Okay, the person that smoked 14 years is much closer to the line, just -1 below the line. So let's find that person. See, there it is. There's the person who smoked 14 years. You can see very close to the line, very small error comparatively. And so that's what we did. We just calculated each one of these vertical distances quickly using our calculator. You could, of course, do it by hand. And on the test, I might ask you, hey, calculate this one by hand so I can see you do that. So let's do that just, how about on, again, that first point. Okay, so my first point was 2220, right? That was my first point. Let's calculate by hand the residual or error. So the observed y is 20. Now I have to subtract the predicted y. So the predicted y forgot what the slope was, 1.85, that's right. Right? So that's how I would do it by hand. Okay. And when I do that, I would get approximately -10. Okay. So at the x coordinate of 22, I have an error or a residual of -10. And so that's why when, oh, I haven't made the plot yet. Let's actually make the plot. Okay, so the plot, I'm leaving x as x, but I'm going to change my y to the errors or the residuals. That's going to become my y coordinate. Okay, zoom stat. Let's turn that line off. And there's the residual plot. Okay. And now I can again trace these, and there's the point I was just talking about. So the person who smokes 22 years, 10 units below the line. And you can scroll through, and there's the person who smokes 14 years, roughly 1 unit below the line. So on and so forth, right? These people above the line. So they've damaged their lungs more than we predicted, right? The people below the line have damaged their lungs less than we predicted. And that's how you make a residual plot. Okay. Now, the key thing on that residual plot is how do you read it? Okay. So let's say I had some data, and let's say the data is clearly curved. So something like that, you know, maybe exponential. When I do linear regression on it, there's no calculator command, you know, it's not going to jump up and say, hey, don't do linear regression, this is curved. No, that's for your human brain to figure out, right? So if you were to do linear regression on this, you would get some line like this. But you just put a line through a curve. That's not a good move, right? You've messed up. Okay. And I've made it obvious, hopefully you would see that even without the residual plot. Okay, but when you then transform this to a residual plot, right, you would see this point's way above, and then we go below, and then we come back, something like that. So when my residual plot shows a curve, it's telling me I put a line through a curve. It's that simple. Now, when do I really need the residual plot? Well, on this one, not so much. It was kind of obvious from the get-go, but I might have something that has just a very, very, very slight curve, right? Something more like that, which my eye, especially with a calculator, may not see. So then when I make my residual plot and I'm zooming in, I'll see a real obvious curve that may not have been so obvious on the original plot. That's the point, right? It's magnifying those errors, which highlights the curve much easier, makes it much easier to read. Okay, so that's the number one thing you're doing on that residual plot. Do you see a curved shape? If so, the data was curved, not linear. So go to chapter 4, right? All right, the other two things you're looking for when you make your residual plot. Well, more than two, but you might, actually let's start with this. you might see something like that. Okay? If that's your residual plot, you're throwing a party. That means that your data was linear and you have a nice close fit throughout the entire data set. So your prediction equation is a good equation. You have a good fit, right? But you might see something like this, okay, where in the beginning it looks really great, but as X is increasing, I'm seeing more and more spread. Notice this is not a curve shape, but it's telling you, again, the human with the brain, that predictions over here are likely to be much more accurate than predictions over here, right? And the overall correlation is kind of an average of all of this. So over here, the correlation would have been much stronger, over here, much weaker. So again, you have to interpret this with caution, depending on where you're trying to make a prediction. Okay, we call this fanning. This is a residual plot showing fanning, meaning as X is increasing, right, our variance is increasing. It could also go the other way around. I could have a residual plot running out of paper. I could have a residual plot that starts off with a lot of variation, and then as X increases, it becomes you see less variation. So more accurate over here, less accurate over there. So those are the things you're looking for. Curve shape, fanning, or the best. The best is a nice random scatter. If I see a nice random scattered residual plot, that means my line fit the data very nicely. There's nothing changing throughout the data set to worry about. Okay? All right, ladies and gentlemen, hopefully that was educational and informative. If you have questions, stop by my office hours and ask. Thanks.